Hello students, welcome back. We're going to continue where we left off last. There are 9 fatty acids that you need to know. We've gone over the 4 saturated fatty acids, and we've gone over 3 of the 5 unsaturated fatty acids. 2 of them are monounsaturated, and 3 of them are going to be polyunsaturated. We've gone over 1 of the polyunsaturated ones, linoleic acid. Now we're going to go over our remaining 2 polyunsaturated fatty acids. Okay, let's move this out of the way. Okay, and let's start here. We already have our chart drawn to save some time. Okay, first, let's look at the number of carbons. This fatty acid is going to have 18 carbons. Its simple number name is 18:0. Excuse me, no, not 18:0, 18:2. Its complex number name is 18:2. Delta, no. We've already done 18 delta 2. This is going to be 18:3, and so the complex number is 18:3. I don't know why I'm doing this wrong. Delta 9, 12, 15. Delta 9, 12, 15. So now if we drew this fatty acid, it would look like this. HO. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and our double bonds would be here. And so this double bond is saturated at 9, 12, and 15. And so that's our fatty acid, triunsaturated. So the systematic name of this one is going to be 9, 12, 15, octa, because 8 octa deca 10, so that's 18 octadeca tri N, because it's an alkene. There's a double bond, trienoic acid. That's the systematic name of this polyunsaturated fatty acid. And the common name is going to be linolenic acid. That's the common name. And so this is our only triunsaturated fatty acid. So it is a polyunsaturated. There are 3 polyunsaturated. Linoleic, which has 2 double bonds. Linolenic, which has 3 double bonds. And now we're going to go to our remaining one. Okay, let's go here. Okay, this one is going to have 20 carbons. 20 carbons. And the simple name is going to be 20:4. There are 4 double bonds in this one. And where are those double bonds? We can get that with the 20:4 with the complex number name. And it's going to be delta 5, 8, 11, 14. Okay, now the structure of that one. HO, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, no. No. I'm wrong in a lot of ways. 1, 2, 3, 4, 5. Okay, here we are. So that's 5, 6. Actually, I'm going to start this all over. So that did not start out well at all. So HO 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then here are our double bonds here. There are 4 double bonds. At 5, 8, 11, no. At 5, 8, 11, and 14. Okay? And the name of this one, wow, this is going to be a big one. It's going to be 5, 8, 11, 14, 20 is icosa. And so this is going to be icosa because that's 20. And then 4 double bonds. Tetra, this is for the number of double bonds. Tetra N-oic acid. Icosa tetra N-oic acid. That's the systematic name. 5, 8, 11, 14. Icosa tetra N-oic acid. Now this one is kind of special. This fatty acid, well, let's name it first. This fatty acid is called arachidonic acid. Arachidonic acid. Now this arachidonic acid can go on to make things like, I'm just going to put these here, can go on to make things like prostaglandins, and prostaglandins and other molecules that have 20 carbons, they're called icosanoids because they have 20 carbons. And these are our icosanoids, the 20 carbon compounds. Yeah, icosanoids are, put that here, 20 carbon compounds. These are our icosanoids. Okay? And so that completes all of our fatty acids that we need to know. 18, 3, delta 9, 12, 15 is linolenic acid, a polyunsaturated fatty acid, and a 20 carbon polyunsaturated fatty acid with 4 double bonds is arachidonic acid. Arachidonic acid is the precursor for many other molecules called icosanoids, and we may talk about them later on. I don't know why it's called arachidonic acid, maybe because it was first discovered on a spider, but I'm not sure about that. And so that concludes the structure and the names of our 9 fatty acids. Okay, students, we're going to continue with our next molecule. Let us go back. Okay, we've discussed our 9 fatty acids. Now we're going to look at glycerol, seemingly a very simple molecule. Let's look at glycerol. So we're going to draw the structure of glycerol here. I'm going to move this out of the way. Okay. Now glycerol, CH2OH, CHOH, CH2OH. And this is glycerol. And glycerol is achiral, so you could number it 1, 2, 3, or you could number it 1, 2, 3, or 3, 2, 1. And because these two, I'll make them red. These two terminal carbons are identical, seemingly. They appear to be identical. Now, glycerol, the most common substitution for glycerol is going to be a phosphate group. And so let's draw this. Let's draw glycerol here with a phosphate on it. And so I'm going to draw it in the Fisher projection. CH2OH, COH, H, and CH2OH. Okay, this is glycerol, but now what we're going to do, we're going to put a phosphate on. So I'm going to erase this here. I'm going to put OPO3. And so there's our phosphate group on the glycerol. Now, drawn this way, if we look at this, this is going to be, since we have the OH here, this would be L-glycerol phosphate. Okay. We could draw it that way. Let's see if that's the one I want. But that's not the one I want. Yes, that's L-glycerol 3-phosphate. Now what I'm going to do, I'm going to take this same glycerol molecule. Let's see if I can grab it. I wish I could. I'm going to just grab the whole thing then, because I need to show you something. I'm going to take this whole glycerol molecule. I'm going to group all of this together. I'm going to copy it here. I'm going to take this glycerol. I'm going to actually delete it in a minute. What I'm trying to do here is show you the problem that biochemists have with this molecule. And so here we have L-glycerol 3-phosphate. And what I'm going to do here, I'm going to take this glycerol and I'm going to flip it over. There we are. Okay, I'm just flipping it over. So it's the same molecule, I'm just turning it 180 degrees. So I'm going to delete that and redraw it 180 degrees. So now my OH is going to be here, H is going to be here. I'm going to have CH2, CH2OH, and OPO3. Now this, since we have our OHs on the right side, this is D-glycerol. D-glycerol 1-phosphate. And again, this is the same molecule. It's the same exact molecule. But because the parent compound was achiral, it was completely asymmetrical. There was no way, there was no numbering system already established. And so the same molecule you can name as an L compound, L-glycerol 3-phosphate, or as a D compound, D-glycerol 1-phosphate. And so this is the problem with glycerol. And so scientists, biochemists, had to come up with a way to deal with glycerol, to give glycerol some direction in life, or give it some directionality. And so this is the problem. Which way is right? And so because they're equivalent, scientists said they have to come up with a whole new naming scheme, for a whole new numbering scheme for naming glycerol and its derivatives. Okay, and so that's what we're going to deal with. I'm not going to try to put that on this clip. We're going to deal with this on the next clip. We're going to figure out how do biochemists deal with a compound that has no chirality. And that's what we'll do next. Okay, let's look at glycerol. Let's draw glycerol again. And let's see if we can give it some sort of directionality. And so this is going to be glycerol. C. These don't matter. H, H, C. Okay, we're going to do it in Fisher projection. Okay. Now, since glycerol is achiral, I'm going to change the color of the two carbons on the end so we can see these. I'm going to give it, I'm going to have the blue carbon and the green carbon. And so, since glycerol is achiral, it would seem that the two carbons, the green carbon or the blue carbon and the green carbon, are the same. But they are not. They're not the same. And the difference has to do with chirality. Imagine this. Imagine that we did something to the blue carbon and gave it a higher priority. So you give this carbon a higher priority here. So I'm just going to circle it. So we substituted something, and we gave, and it left the blue carbon with a higher priority than the green carbon. And so then this carbon here, which is now, well, before we change anything, it's achiral. But if we give this one a higher priority, that's going to become, this carbon is going to become chiral. And it's going to be, well, in this situation, that's there, one, two, that's going to be R. So this would be an R compound. So this would be R something. And so this carbon would make this compound an R compound if you substitute, if you gave this a higher priority. If you gave this blue carbon a higher priority, this would be an R compound. So we call this carbon the pro R. What's the wording? Yeah, nothing special. Just the pro R position. So we call that carbon the pro R position because it would make this achiral. So this carbon is achiral, but it's going to become chiral. So we call this carbon prochiral, or right before chiral. And so if we gave the green carbon, if we gave it the highest priority, if we gave it a substitution to give it the highest priority, then this compound would become an S compound. And so we call this the pro-S position. And that's very important. Now, numbering. Before you even make any substitutions, if the carbon the pro-S carbon is always the 1 carbon, so we give it the 1 position. This is the in glycerol. This is the 1 position because 1 goes with pro-S. Whatever substitution makes that compound an S compound, that carbon is the 1 carbon. And so this would be the 2 carbon, and this would be the 3 carbon. And so even before we make any substitutions, the carbons in glycerol, which is achiral, has a specific numbering. And so we call this type of numbering of glycerol, it's based on stereochemistry. And so we call this stereo-specific numbering. Or SN. So this would be, well, this would be, I guess we could call this SN glycerol, but it doesn't have, because I've numbered it. So this is stereospecifically numbered glycerol. But we haven't given it any substitutions. Now, if we were to substitute this glycerol, the glycerol that's found in us, in humans, the phosphate, the glycerol phosphate that's found in humans, is added to the pro R. It's added to the pro R carbon. And so that'll be carbon number 3. So if I were to draw, I don't know if I have room. I don't know if this is if I'm gonna be able to grab that. I'm not gonna be able to. So I'm gonna have to go to a new, let's make a new slide. Actually, I want to just copy this one over. So I made a new copy of this one, and I'm going to actually erase. No, I want to start on a new slide with that one. So we're going to stop here. Okay, now we're going to make glycerol phosphate. This is a very important compound in the body. It's an important intermediate for lots of other compounds. And so we need to figure out, does the glycerol we have in our body, is it is the glycerol phosphate that's in our body, is it S-glycerol phosphate, or is it R-glycerol phosphate? And so let's just draw glycerol again. So CH2OH. COH, H, CH2OH. Okay, now let's figure out which carbon. I'm going to be erasing which carbon. Well, so let's do this here. Let's still make ourselves. Let's make this one blue and make this one green. So, which position is this? Okay, the blue carbon, well, I shouldn't make that color. The blue carbon is the, so the blue carbon, actually, what I'm going to do, I think I'm going to put that OH on the other side. Yes, I'm going to do something here. I'm going to put this OH over here. And the H here. And so now the blue carbon, so if the H is there, This is the pro-S position. So this is pro-S, and so that means by default this has to be pro-R. And the reason I do this is because I can just simply number these 1, 2, 3. And in our body, the glycerol phosphate is going to be R. And so that means CH2OH. That means that the phosphate needs to go on the 3 carbon. So 1, 2, 3. And we don't call this R-glycerol. We call it stereo SN, stereo-specific numbering, or stereo-specifically numbered glycerol 3-phosphate. And that's how we get around the whole problem of numbering for glycerol. You don't have to worry about D or L. It's always SN, because you have to use stereochemistry to figure out which carbon is 1, which carbon is 2, which carbon is 3. You know, we've already gone over this part, but just again, the carbon that gives you an if it increased in priority, if it gives you an S configuration, that's the pro-S carbon. If the carbon, which is green here, if increase in priority gives you an R configuration, that's the pro-R carbon. And the achiral carbon, before there is any chirality, this carbon is called the prochiral carbon. And you can think in this case, pro means before. And so pro-S is before S because it's not yet S. Pro-R is before R because it's not yet R. And prochiral is before it becomes chiral. And so it's prochiral. And so this is how you name glycerol phosphate that's in the body. It's glycerol. It's SN glycerol 3-phosphate. That's the glycerol that we'll have in our body. And so when we start making our glycerol fatty acid derivatives, we'll be using SN glycerol 3-phosphate. Make sure you understand this for your test. This is an important concept in biochemistry.